Hi, everyone, and welcome to our webcast, Design Alternatives Using CATIA's Product Engineering Optimizer Workbench. Our speaker today is Yuri Apavanich. Yuri, the floor is yours.
Good afternoon, everyone, or should I say good morning to those in the Pacific Coast. Welcome to our webcast. It's one of the series of our webcasts we're running through the year. And pretty much the main goal of those webcasts is to familiarize CATIA users with something that is not exactly mainstream in CATIA, yet could be very, very useful. So in the past, we've done things such as composites and some finite element analysis, et cetera, et cetera. Today, we're going to talk about a workbench which is called Product Engineering Optimizer. The topics today, we're going to talk a little about CATIA knowledge-based engineering portfolio, and we'll discuss a couple of tools, optimization tool and the design of experiment tool. So I'll be doing a lot of demos because the best way, we believe, to show a product or capabilities is to run through a live example. In the end, we'll summarize what we've learned today, and we'll have some time for questions and answers. If you have questions along the way, feel free to ask using the chat window. Otherwise, we'll leave the questions until the end of the session. Okay? So just a couple of words about CATIA knowledge-aware portfolio. You know, the buzzword is knowledge-based engineer, et cetera, et cetera. The idea is essentially to create smart models. Smart models in terms that they embed industry knowledge, standard practices, et cetera, et cetera. And CATIA in this respect stands apart. It has, we believe, the most comprehensive portfolio as far as knowledge-aware. There are many options available. I'm sure many of you have created formulas and parameters in the past. This is the part what is called CATIA infrastructure. Let's create some simple things as far as design table, et cetera, et cetera. There are plenty of others, such as automation, which is Visual Basic, knowledge advisor, adding things such as rules, reactions, checks, laws, equations, et cetera, et cetera. There's also knowledge expert, product knowledge template that lets you create all kinds of user features, power copies, product templates, et cetera. But what we're going to talk about today is the product engineering optimizer. This workbench is very frequently overlooked, but it could be very, very useful. So we're going to start with the tool which is called optimization. And before we begin, before I do my demo, I wanted to discuss with you what I call ingredients of optimization. So the optimization tool lets you design by go, which means when you want to use this tool, you need to figure out what's the goal. And it could be many different types. For instance, one of the examples might be minimization. That's a very typical, application. We have some load-bearing part. It could be a bracket. It could be a frame. It could be just about anything. An objective is to come up with the lightest design possible. So what you want to do is minimize the mass of the bracket or some other part given the loading condition. So the second type is the maximization. And example here, let's say we want to design a windshield wiper, come up with the best configuration as far as geometry, coordinates, locations of arm and blade, et cetera, et cetera. And what you want to do, the objective becomes maximize the white area. The third type is the target value. So sometimes you want to have your design characteristics to hit a certain target value. A very simple example here, design case, we want to design, well, a tuning fork. So the tuning fork is supposed to have a very specific natural frequency or fundamental frequency. So we want to come up with parameters and dimensions of the tuning fork which will ensure the required natural frequency. So we have to start with a goal. Now, the second ingredient of optimization is free parameters. They're also known sometimes as design parameters, design variables, et cetera, et cetera. So essentially, we want to achieve our goal or objective by picking up the best combination of those design parameters, so free parameters. Again, if we take the first example, minimization of the mass of a load-bearing bracket, Those design variables might be things such as bracket thickness, maybe some bend radii, et cetera, et cetera. If we take the second example, which was maximization of the wipe area, design variables would be geometrical parameters such as wiper arm length, blade length, angles, et cetera, et cetera. And as we speak about the third example we were discussing, the type of the design case is a target value. To ensure required natural frequency, the design variables would be tuning fork dimensions. So that was the second ingredient in optimization. Now, what we also have to have is a relation, which means we need to establish some kind of a relationship between free parameters and the objective. And again, many different options here. It could be something pretty simple, such as a formula. You know, with CATIA, we can create all kinds of formulas and relations. And if we speak of this example with maximization of the wipe area, we can create a formula which is expresses wipe area through the design variables. Fair enough. This is what you can call explicit relation between the design variables and the objective function or goal. It's not always like that. Sometimes you have to have the type of relation of a kind of like a black box. For instance, this example, which requires running FEA, we want to obtain the required natural frequency. We cannot do any hand calcs or any simple closed form solution in this case. We actually have to run FEA to measure the natural frequency of the tuning fork. So the relation becomes like a black box, that there is no simple expression for it, there is no simple formula, and yet we can put this kind of black box relation into the loop for optimization. So that's the third ingredient. Is it all? Not really. You know, in many cases we should have design constraints, which are also linked with relations linked to the free parameters. So what are those design constraints? Again, it depends on the type of the problem we're trying to solve. For instance, if you consider example with minimizing a mass or a weight of a part, the obvious constraint would be, okay, we don't want the maximum stress to exceed the yield strength, and that becomes a design constraint. Another example, so we were talking about windshield wiper optimization. So when we optimize the wipe area by adjusting geometrical parameters, locations, et cetera, what we want to make sure is the minimum distance between the blade and the windshield edges, you know, must be maintained. And that's pretty much it. So once we have all those ingredients in place and we run the tool, what happens, optimization algorithm, and there are several available in CATIA, we'll talk about it a little later. So optimization algorithm automatically, without user involvement, adjusts free parameters in order to achieve objective while respecting design constraints. All right, so let's take a look at some practical examples. Again, I'm going to be using pretty simple models given the time limits, etc., but hopefully they're going to give you an idea how you could use it in real life. Okay, so where is my CATIA? There we go. And I'm going to start with a pretty straightforward model, and that's going to be wiper optimization. So the model setup, let me talk about it a little. So there is a windshield surface, which is this one. It's kind of darker, semi-transparent. It's actually not a flat surface. It has a curvature. It could be pretty much any surface. And there are some other things in here. So for instance, I have the arm, which it's a conceptual model. Of course, it's not detailed, but at this point, when I want to come up with the best configuration of design variables and parameters, it doesn't have to be detailed. I can make it detailed anytime later. So I got the axis of rotation. It's a kind of one blade design. The windshield is sort of narrow a little. So I'm going to try to see if I can come up with a good design just using one arm. So here's the blade, the yellow one, and this surface, the green one, represents the white area. So the model has to be parameterized. So what I've done here, I've created some parameters that control the geometry of the setup. So for instance, if I change blade length, Let's say I'm going to change it to 300 and hit OK. You see the area became larger. And if I change some other parameters, so let's say I'm going to change the angle end. Right now it's 90. I'm going to make it, let's say, 120. Hit OK. You see it's a wider area taken by the blade, and so on. So that has to be done because any optimization has to use parameters, and ability to create parameters is critical. It's essential skill if you want to use this tool. So what I'm going to try to do is to actually maximize this area of the surface. So I'm going to have to create some additional parameters. So first of all, I need to create a parameter which will measure the area of the surface. So we're going to go hit this, and new parameter of type, it's a type area. So I'm going to hit area, new parameter of type, and pick a name. Okay, and I'm going to add a formula. Okay, so I want to measure, there is a measure dictionary, see there is a measure, and there is an option to measure area of a surface or area inside the curve, within a curve, a closed curve, of course. So in my case, it's a surface, so I'm going to do this. Double click, you see the area goes in. Now, which surface I want to measure, I'm going to open up my specification tree, and I believe that was this one. Okay, so we can hit OK. Yeah, it tells me it requires update, which is fine by me. That's exactly how it's supposed to be. And hit OK. Okay. So right now the white area is, what is it, about 0.095 square meters. Okay, fair enough. Now, when I'm optimizing this design, what I want to make sure when this blade, the arm rotates, the white area doesn't come too close to the edge of the windshield. So I need to create a parameter which will measure the distance between the white area and the windshield. So we're going to have to do a couple things, and the first one, I'm going to extract the border of this windshield area. I'm going to switch to generative shape design, and I'm sure you all use this tool. This is called boundary. The boundary of this guy, fair enough. So I need to create another parameter, which is the distance. So I'll hit this. New parameter of type, that's parameter type length, because it's a distance. Okay, hit new parameter, and I'm going to call it distance to edge. Gotta add a formula. Okay, again, it has to be measured, so I'm going to go into the measures. And yeah, there is. You see there is a distance option. So I'm going to double click, and I'm going to measure the distance between the boundary I've just created. That's this guy. Okay, and the white surface. And the white area was this one. Okay, so I can confirm. Yeah, also requires update. That's fine by me. And here is the current distance. So that's pretty much all the prepping. So now I'm going to create an optimization setup. Okay, so I have to switch to the Workbench. Start, as you see, there's a knowledge-aware heading, and there's a product engineer optimize. All right, so the tools I'm going to use is this one. It's called optimization. All right, so optimization type. There are several. You see there's minimization, maximization, target value. By the way, there is an option only constraint, which is like feasibility analysis. But I want to maximize the white area. Optimize parameter. I'm going to hit select. And I'm going to put this. You see there's the white area. And hit OK. So, yeah. Pretty much it shows the current value, fair enough. Now I need to pick the parameters I want to optimize. Okay, so I'm going to hit edit list, and I want to adjust, maybe several locations. The first one, let me put on the design parameters, is going to be the width coordinate of the axis, and I believe that was this guy. I'm going to put it into 3 parameters for optimization. What else I want to optimize? The arm length, it's highlighted, and I want to put it in. What else? Perhaps the blade length. Put it in. Okay, and the angles. So the start angle is right here, and that's the end angle. So I'm going to select angle start, put it into the 3 parameters, and also angle end. Yeah, that's pretty much it. I can add more parameters if I want to, like vertical coordinate as well as blade angle, but you know, let's keep it simple for now. Gonna hit OK. So these are all the parameters, and these are the current values. Now I need to also set up the ranges and steps. So can I run with automatic setup? I can. The problem is if for some reason algorithm picks some weird combination of parameters, the model may not regenerate. This is something I want to try to avoid. So I'm going to hit, let's say, this coordinate, edit ranges and step. INF means inferior, which is lower bound. Sub means superior, which is upper bound, and also option for the step. So let's say for the coordinate H, I'm going to go from -200 up to, 50 is almost the center, so I'll keep it like that. And I want to use a step about 1 millimeter. And so I go. So I'm going to select the second one and ranges and step. So for this one, I want to vary it from, let's say, 150 to, I guess, 250. No, actually, I'm going to go higher, 350. Okay, and the step, also 1 millimeter. That's the arm length. So the blade length, edit ranges and step. Okay, so for this one, I'm going to go, let's say, from 200. These are just the ranges, upper and lower limits. It's 350. So this one is going to go in 1-inch increments. That's the blade length. That's 25, roughly. 25.4 to be exact, but I'm going to use 25. And as far as angle start, right now it is 20 degrees. I'm going to vary it, let's say, from 10 to 20, just in case. Okay, and the step, 1 degree. And so you see it's pretty straightforward procedure. You got to pick some reasonably meaningful values. So this one is going to go from 90 to 120 in 1 degree increments. Okay. So what else? If we scroll to the bottom, there is an option for simulated annealing algorithm with the algorithm type. There are several options. We don't have much time to discuss all the options, but I'll tell you that the simulated annealing perhaps is the most robust and more reliable. So I'm going to keep this one. Okay, so maximum number of updates, just eyeball it, let's say 300. Conversion speed, it's pretty simple model, so I'm going to use medium. Now, what else? I need to create my constraint, which is to make sure that the distance between the blade and the edge is maintained, let's say, greater than 20 millimeters. So these are constraints. I'm going to create a new one. Again, it opens up the formula editor. So I'm going to pick a parameter which is distance to edge, and I want to make sure it's greater than 20 millimeters operators. So let's say greater or equal than 20 millimeters. Okay, that's my design constraint. Yeah, that's fine by me. And I think we're ready to go, if I'm not mistaken. Let me just double check the first one. So we're using simulated annealing, minimum, save optimization data without visualization update to speed up. Yeah, sure did. Okay. Let's hit run. It's going to ask me where to save the result. We can save it to Microsoft Excel, but I do recommend using text file. It's just much faster. It doesn't have to invoke a style, etc. So I'm going to use, let's say, log. When I hit run, it starts computation. Hopefully it doesn't take too long. In the meantime, I am going to check if I have any. I can't even see that. Yeah, so it says does iterations. It's looking for the best possible combination. You see at the very top it shows the number of updates performed. By the way, you see the constraint is satisfied at this point. It kind of runs through different options, etc. And there you go. So basically, that's the design it was able to come up with. Okay, and as you see, the area, well, almost doubled. I think I had about 0.09, so the white area is almost doubled. And these are the dimensions it peaks, and I can also review computation results. So we can actually visualize, you see there it did a whole lot of different evaluations, and it showed all kinds of parameters and what was happening here. We can visualize it using curves. So for instance, if I want to see, well, actually what I want to see is instead of results to display all, I want to see only results with satisfied constraints. Okay, so I'm going to select a parameter and I want to see how those things are changing. So I'm going to use white area. Okay, and yeah, just one. We can visualize several. Now when I hit throw curves, as you see, it was using, you know, it's a process. It's going to going back and forth through all kinds of combination of dimensions, et cetera, to come up with the best solution. Is it a totally ideal solution at this point? Not necessarily. You know, as any algorithm, it has its own limitations, so I might want to refine this solution if it was in real life, and if I restart this optimization at this point, it will simply take the current configuration with already increased area and try to maybe come up with even better solution. That could be affected also by the convergence speed. I use medium. If I use fine or slow rather, okay, then the result is even better, so it's more refined. All right, so and if I want to go back, let's say if I want to go back to computation results, I want to go back to my original configuration. That was attempt number 1, apply values to parameters, hit OK, and as you see initially that was my area. Okay, so that was my first example. I'm going to do another example. I'll run several. And the second example will be not necessarily an obvious application of the optimization. Let me explain the setup. Okay. All right. So the model is pretty much as simple as it gets, but here's the deal. Okay. So the model represents it's a flexible hose. There are a couple of fittings at the ends, and that's a hose, which is modeled using a spline. Okay, the length or the shape of the spline is controlled by a parameter which is, let me get it, let me show you. Okay, so there is a 0.3. Actually, I'm going to make it visible. So I'm going to use, let's say, this symbol. You see there is a point in the middle. Essentially, this point defines the sag of this flexible hose under its own weight. Now, what I want to do here is to make sure that the length of the configuration of the spline is selected based on the standard length of the hose. And let's say the length of the hose comes in 50 millimeter increments. So it could be 600, it could be 650, 700 millimeters, et cetera. So how do I make sure, you see I have a couple parameters here. That's a standard length. Okay, so I created a parameter with multiple values. But as you see, it doesn't match the actual length. So of course, I could go through a lot of pain, which is trying to adjust location of this point, moving it back and forth until it kind of matches here, but there is a better way. I'm going to use optimization. So how we can possibly use optimization? Well, what if we set up our goal as the difference, or to minimize the difference between the standard length and actual length? So the minimum would be 0, right? And if we run optimization, then it will try to match the actual length by adjusting location of the sag point to the standard length. Let's try to do that. So we need to create a parameter, additional parameter, and this parameter will measure the difference between the two, the standard length and actual length. So as always, going into parameters, new parameter of type length, yeah, sure deal. okay, and that's going to be length difference, okay, and we're going to add a formula. So first of all, the actual length can be longer or shorter. So what you want to do is take absolute value. So I'm going to go into the math. See, there's a whole lot of functions here, but I'm looking for absolute value. Yeah, there you go. There's abs. Okay, so I'm going to double click on this function. And what I want to measure is the difference between standard length and actual length. Okay. Now the abs function, when working with CATIA knowledge, where you got to pay attention to the units. You see, it takes number without units, so I'm going to have to do some unit conversion, which is as following. Those who work with Knowledge Advisor will know exactly what I'm doing here. So I'm taking the difference or a difference in length, dividing by 1 millimeter, I make it without units, and the total, okay, so then I take in real number and interpret it as millimeters. Okay, that's my length differential, and that's exactly the case. You see the standard length is 600, this one is 639, and the length differential is 39. I think I'm ready to do my setup. Okay, so we're going to switch to the KnowledgeWare Product Engineering Optimizer. Select optimization. Okay, fair enough. We want to minimize. Yes, we want to minimize. Okay, so that's going to be length difference. Okay, which parameters we want to change? Okay, that's going to be the location of the stack point, which is right in the middle. So we can click on it. And location, I think coordinates was Z, that's vertical coordinate. That's what we're going to adjust. Okay, do we want to set up ranges? I'll just use automatic setup, fair enough. Simulating on the algorithm, good enough. There is no problem with that. Do I have any constraints? Actually, no. That's an example of so-called unconstrained optimization. I don't really need any constraints at all. So I think I'm ready to go. Do I want to save optimization data? Maybe not. That's a very straightforward model. Let me run optimization. So it starts computation. As you see, it kind of changes those numbers. And as you see, the length differential gradually goes to 0. It's actually kind of randomized algorithm, simulated annealing. Okay, so there you go. Let's see what we got. I'm going to hit OK. And yeah, you see the difference is 2/10,000 of a millimeter. So I kind of pretty much made my shape of this hose match the standard length. Now, what if I pick a different standard length? I'm going to double click. And instead of 600, I'll select, well, 700. I have to rerun optimization. Okay, so I can go into the optimization, double click, and run it again. So now it's going to match the new length, which is 700 instead of 600 millimeters, so the standard length of the hose. All right, so what do we got? Let's see. Yeah, again, 700. Well, that's kind of not a very elegant way of handling this. So I guess we can improve it, which is, let's say, what do we want to have in this model? Whenever user changes the standard length of the hose, the optimization runs automatically. And this can be accomplished with reaction tool. So I'm going to have to switch to KnowledgeWare Knowledge Advisor. Okay, and I'm going to create reaction. Now, this reaction is going to fire whenever the user changes the standard length. I'm going to select this parameter. The available event is a value change. Fair enough. Now, what I want to do is hit edit action, and I want to run optimization. Okay, that's like a little VB script. And the first thing I need to obtain the path within the CATIA model to optimization.1. So I'm going to click Insert Object Resolution. Okay, so basically at this point, this identifier optimization1 gets me access to this one that I want to run. But I still need to run it. Okay, so I'm going to open it up. I'll show you where to find it. If you ever done any automation with Visual Basic, so that's a CATIA help system for automation, object, Visual Basic, etc. And I am looking for optimization. Yeah, Product Engineer Optimizer. There it is. Okay, so let's see what this guy has. Optimization, and there's a function run. So that's what I'm going to have to use. So I'm going to click on the hyperlink, and as you see, the run requires one input parameter or argument. It's a Boolean, whether or not to use stop dialog. Okay, so I'm going to use a stop dialog for this model. Okay, so I'm going to go back to CATIA. So all I got to do is optimization 1. It's important not to make a typo. I'm going to put dot run, so I want to run it with stop dialog. Is it correct? No typos? Hopefully not. Well, we'll find it out very shortly. And that's pretty much it. So now I have a reaction. Again, what's the sequence of events here? If the user changes the standard length parameter, it will trigger a reaction, and the reaction in turn will trigger optimization. Let's see if it works. So I'm going to select a different value. Yeah, it works. It seems to be working just fine. So it's trying to match the new one, which I set up to 600 millimeters. Does it work? There you go. So you see the lens differential is extremely small. I can confirm, and I have actual lens, which is 600 millimeters. Okay, so basically, the reason why I showed you this example is that, when you say optimization, people tend to think that's the way to optimize design. Not necessarily. So here, I essentially used optimization to design a small assembly. So this is something that you guys should not overlook. And I'll quickly run a third example. I do have a couple more demos, but we seem to be on time, so I'm going to close this one. So with the third example, I want to show you how to link optimization with finite element analysis. If you recall, if you've used finite element analysis in CATIA, it's a different type of a document, which is analysis document. So I'm going to open analysis document. It's a simple bracket. So the bracket is, it's a sheet metal part. You see it's fixed on the this surface, and the vertical load is applied. All right, so I kind of pre-run this not optimization, but analysis, but let's take a look at the stresses, okay? So the stress is 341 megapascal. Does it exceed the yield or no? Okay, let's check it out. Gonna hit this. And the material property, you see the yield strength is 250. Not good. So, of course, I could kind of make my guess estimate here. Okay, should I work with thickness? Should I work with radius? But what I should notice at this point is actually where the area with the maximum stress happens. It's exactly on the bend radius. So I'm thinking, okay, possibly I could reduce the stress by making the part thicker. But maybe I could reduce the stress as well, just making the radius larger. Now, the best way to do it is actually create optimization, okay? I'm going to get rid of these. And again, you got to do some prepping, which is creating parameters. Now, I'm going to need two parameters. One is, so basically the setup I'm going to be using, I'll be trying to get the minimum weight of this part while respecting design constraints. With design constraint is that the yield stress is or the stress, maximum stress is less than the yield stress. Okay, so I'm going to have to create a couple parameters. I'm going to hit that. The first parameter I need is the mass. So that would be the mass, new parameter. So bracket mass, got to add a formula. So mass is volume times density. Okay, so if I go into the part measures, there is a volume option. And what I want to measure is the volume of the part body. Okay, times, I need to get access to the material properties. So I'm going to put a filter on steel. You see there's a material applied. And there is my density. Okay, so when I hit OK, I can check it out just in case. I see there's a parameter created, and that's the bracket mass. So right now it's about, what is it, 0.05 kilograms. I also need a second parameter, which is the maximum stress in the model. Okay, so I'm going to hit it again. New parameter of type, and that would be pressure, same unit as stress. And I'm going to call it maximum stress. Okay, fair enough. I'm going to hit add formula. So there's the analysis operators. Energy, displacement max, frequency, global error, background factor. The one I'm looking for is maximum one-meter stress. So I'm going to double click on this guy, select study case solution. And that's pretty much it. So as you see, the maximum stress is 340, and I want to make it under the yield stress, which was 250, if I'm not mistaken. All right, so now we can proceed to optimization setup. So that would be knowledgeware, product engineering optimizer. Optimization, so we want to minimize, what do you want to minimize? We want to minimize the mass, bracket mass. Okay, so that's the current value. Now, which parameters I want to use for optimization? I'll use two. That's the sheet metal part, so I'll try to work with the thickness as well as the bend radius. Okay, so I'm going to hit edit list, put the filter on sheet metal parameter. So the first one is going to be thickness, fair enough, and the bend radius. Okay, fair enough. Now, do I need to adjust the ranges? I guess I do. Okay. So I'm going to hit this fella, edit ranges. So the thickness, let's say I want to check between 1 millimeter and 10 millimeters, just in case. I don't know how far it will need to go, so I'm going to set up a pretty generous range. Okay, and for this one, right now it's 4 millimeters, and I'm going to try to work, let's say, from 3 and all the way to, well, okay, 8 millimeters. All right, second step, I got to take care of constraints. Okay, so I want to make sure that my maximum stress is, this guy is less or equal. Okay, and I'm going to put a filter on the material. You see there is a yield strength, just like that. Okay, so maximum stress should be less or equal than the yield strength, or just plain less. It's up to me. Actually, I'll make it, let's say, like that, less. Okay. 8 complaints. Okay, in optimization constraint, the right number must be numeric and have a correct magnitude. So I cannot put a parameter on the right side. But there is a solution, which is, what if I, instead of setting this equation this way, I can say that the maximum stress, negative, the yield stress should be less than 0 MPa. It's equivalent, right? So if max stress is less, it's going to be negative. If it's greater, that's going to be positive. I requesting the difference to be always negative. Okay, so now when I hit OK, it takes it just fine. And actually it says, yeah, right now it is violated. Okay, if you recall, the max stress was about 340, the yield was about 250. Okay, so let's set up the rest of the algorithm. I'll use fast. I don't want to spend too much time. We'll limit it to maybe a few iterations, again, just to make sure we're not running out of time. Consecutive updates without improvements, 5, yeah, let's just think about it, okay? And we can hit run optimization. Again, it's going to ask me to save the results. Okay. And it starts computation. So I'm running without visualization update. Visualization update takes longer time. So let's see how fast it goes. It should be under 5 minutes, hopefully less than that. Okay. Yeah, so it's 12th iteration right now. I mean, whenever you have FEA in the loop, it always takes longer time. And actually, if you want to do something like that with something that takes quite some time to compute, there's an option to create a batch, which is you set up your model, prepare parameters, etc., and then just run it overnight using batch mode. So that's something that could be quite useful. But hopefully this one runs. So what is it, about just over 1 minute? If I'm not mistaken, it should take about 2.5, 3 minutes, so hopefully. Now let me see if we have any questions. No, not at this point. Okay. Okay, let's wait. I don't want to interrupt it.
Yuri, while this is running, someone did ask a question. They asked where do you find this license?
Well, it's a separate product. The acronym is PEO, Product Engineering Optimizer, and it belongs to the KnowledgeWare domain. So if you go into the Start menu, scroll down to KnowledgeWare, you should see that license there. If you don't, then perhaps you don't have the license. And you might consider it. I know many big companies have it, like for instance, most of the automotive OEMs and the aerospace OEM, they use it quite extensively in R&D, et cetera, et cetera. For instance, Honda has it for sure. I know Ford does as well. Other companies such as Toyota, Honda, et cetera, just check. It could exist as a shareable product as opposed to a part of configuration. On my laptop, I'm running what is called all-in-one license, which is pretty much all products available to me. Okay, so 50 iterations. Yeah, so 50 iterations took about 3 minutes. So let's see what would be the optimum. Well, it turns out that the best combination of those two it was able to find, you see the thickness was about 2.6, and band radius is 5.4. And it's kind of odd number, et cetera, et cetera. And by the way, let's see the maximum stress. I'm going to scroll down. Yeah, it's 247. See, it's just under yield. All right, so what if you have to work with rounded numbers? For instance, well, I cannot use 2.6. I have to use, let's say, 2.5 millimeter and then 3 millimeters. The recommendation is at this point I can lock one of the parameters, for instance, thickness, and then optimize just the remaining parameter, like a band radius. So this is something you have to do sometimes. I don't want to do it. We don't really have the time. Hopefully that kind of rounded off the presentation optimization. Okay, we still have some time. The time is running short, but anyway, the other thing I wanted to show you real quick is a very interesting tool, which is design of experiments. So I'm going to run just one demo. In general, what is design of experiments? It's a tool that enables you to experiment with various parameters of the system and study their interaction and influence. So in simple words, it lets you determine cause and effect relationships. Like how this picture shows here, you have some system and you don't really know its behavior. It could be, not as obvious. So you set up some controlled input parameters, which are varied according to user-specified metrics of experiments, and then you observe and record output responses. Why you want to do that? Well, these are several typical applications. You can quantify influence of the input factors onto the output responses. You can also determine interactions between the input factors. It enables you to create predictions, and also you can identify most influential factors parameters to be used in optimization to speed up the process. So hopefully we still have time to do this one. So what I'm going to do is, let's say instead of doing optimization, I want to see or determine prior to an optimization, should I maybe mostly working with thickness or the bend radius. So I'm going to go back and restore the initial parameters. I'm going to go into my optimization, computation results. That was the first, the initial parameters, apply the value to parameters. So it kind of recomputes everything back. Yeah, so pretty much I'm back to square one. I see the maximum stress is back to 340, dimensions back to 2 millimeters and 40 millimeters bend radius. I want to explore. So I'm going to set up design of experiments, okay, and the input parameters I want to explore, those will be those two guys, which is the thickness. So I'm going to put, hit edit list, put a filter on sheet metal parameters. I want to study thickness, and I want to study bend radius. Okay, now I need to take care of the ranges. For this setup, I have to set up ranges and number of levels, okay? So essentially it creates like a matrix of experiments. So as far as the thickness, let me try to go from, let's say 1 millimeter and all the way to 4 millimeters. Number of levels, I'm gonna make it 4. So it's, 1, 3, well actually, I'm gonna go to make it faster a little. Of course, in real life, you want to have more levels, but the time is short, so I'm going to do this. So, okay, fair enough. And for the bend radius, modify ranges, so I'm going to go, let's say, from 3 to 6 in incremental 1 millimeter, so there's going to be 4 levels. Now, what I want to observe? Well, I want to observe, first of all, the weight, the bracket mass, and also the maximum stress. And that's pretty much it. Okay, so without filing, and I can run design of experiment. So it's going to ask me where to save. So I'm going to use text file. I'm going to use, let's say, DOE as a name. Hit save, and it starts computation. So number of levels in my case was 3 and 4, so 3 times 4 is going to have to do 12 computations. Should take about 2 minutes if I'm not mistaken. Okay, let me check other questions so far in the chat. Nothing yet. Okay, what is it, about 30 seconds elapsed. Hopefully it's going to be quick. So again, as you see, the values change, and as you observe what's happening. Yep, that's pretty much it. So let's take a look at the results. So essentially, as I was saying, it performed 12 calculations, and these are the levels, etc., and it shows me the values. Now, looking at the result this way, it's not very useful. Best if you to do it using a curve. So let's say I want to observe how the maximum stress depends on the thickness. Okay, see effect of the thickness on maximum stress. If If I select that, oh, there you go. So as you see, the effect is quite substantial. It shows three curves. The yellow curve is the mean effect. The red one is the max effect, which is mean plus 3 sigma, which is 3 standard deviations. And minimum effect is the mean minus 3 sigma, which is standard deviation. So as you see, the stress depends a lot on the thickness. Okay, that's kind of first type of information we can get. What about the second one, which is how the max stress depends on the bend radius? And as you see, the effect is not as pronounced. See, basically, we're looking here at the slope of those curves. And if you recall, for the thickness, they were pretty steep, which means we can deduce that, yeah, okay, there was a lot of influence of the thickness onto the maximum stress, which is kind of expected, but nevertheless. And as you see, the effect of the bend radius is a lot more muted. All right, we can take a look at some other things. Let's say another thing is we want to see the thickness on the bracket mass. Well, kind of as expected. We make it thicker, the mass goes up, and it depends a lot on that. And this one, so bracket mass bend radius, again, you see the bend radius has very, very muted influence on the max mass, which is kind of expected. We can also observe the correlation between the parameters. So we're going to go to which one? Force interaction between thickness and bend radius. Okay, and this was, I believe, was it maximum stress? Let me take a look. Yeah. Okay. So you see, that's the bracket mass, by the way. Okay, and as you see, the bracket mass essentially, see, these are different curves for the bend radius. We can zoom in, but as you see, okay, let's go back. Okay, this way. Okay, let me zoom in. Okay, as you see, the mass very little depends on the bend radius. It mostly depends on thickness. Again, kind of as expected. And lastly, well, we only have a few minutes remaining. We can make predictions. So once we kind of deduce from this model, yeah, okay, perhaps we should work mostly with the thickness rather than the bend radius. Let's check out what's going to happen. So essentially, the design of experiments tool internally creates what you can call mathematical model of the system, which uses for the examination of results or predictions, making predictions. So we kind of determined that the bend radius has very little influence on the maximum stress. So I'm going to change this value on, instead of 2.5, I'll make it, let's say, instead of 2, about 2.5, and I'm going to run prediction. And there you go. So as you see, the maximum stress went down from 340 to 240, but of course the mass went up a little. Okay. So I guess that's it with my demo. We do have a few more minutes remaining. Karine?
Hi, Yuri.
Do we have any questions at this point?
I don't see any others. So just a reminder, if anyone does have a question, they can post it in the chat window or Q&A window here in WebEx.
Okay. Well, if no questions as yet, I'll give you guys a few more minutes to think. So I'm going to kind of do a bit of a summary here. So we've seen software demonstration, etc. So what I wanted to say as a summary. CATIA, in our opinion, offers the most complete suite of tools and workbenches for what is called knowledge-based engineering. And I kind of happen to work with many different types of CAD software. To me, CATIA is unparalleled. So Product Engineer Optimizer allows engineers to explore design alternatives and accurately optimize design. By enabling, first of all, you can do virtual experiments in order to evaluate parameter interactions and make design predictions. And the second, what you can call design optimization by Go. That's optimization tool. Lastly, if you want to get in touch with us, I believe we are recording this webcast, so you can review it at any time later. If you have any questions or request more information about this Workbench and anything else, here is our contact information. We offer anything about CATIA. We are the sole official solution partner, which means training, software, consulting, you name it, and this is our contact information here.